You clicked because you want to understand why your new GPU is underperforming in modern AI workloads. The reality is that raw processing power numbers are lying to you about what actually limits performance today. By the end of this explanation, you will know exactly which hardware specification dictates whether your model trains efficiently or stalls completely. For years, the industry has operated on a simple assumption. If we build faster processors with more floating-point operations per second, our models will train and infer faster in direct proportion. Engineers buy top-tier graphics cards like the H100 or RTX 4090 based entirely on these FLOPS specifications, expecting linear performance gains as model complexity grows. This mindset has driven purchasing decisions for over a decade, but recent research from UC Berkeley, ICSI, and LBNL proves that this foundation is fundamentally broken. The primary bottleneck for modern artificial intelligence is no longer how fast the processor can calculate. It is how fast data can move into that processor. Here is the thing about memory bandwidth versus compute power. We are witnessing a massive divergence in scaling rates that has created what researchers call the memory wall. While server floating-point operations have tripled every 2 years, DRAM and interconnect bandwidth have scaled by only 1.6 times and 1.4 times respectively over the same period. This means your processor is becoming exponentially faster than its ability to feed itself data. The result is a system that spends most of its time idle, waiting for information to arrive rather than performing calculations. This disparity becomes especially critical when we look at decoder-based transformer models during inference tasks. These architectures require massive amounts of parameter access relative to the actual computation being performed. When you run these models on standard hardware, the memory systems saturate long before the compute units reach their full potential. The processor sits there starved for data while generating heat from sustained attempts to move information at maximum speed. This creates a thermal inefficiency where the GPU acts as a heat-generating engine driven by I/O overhead rather than calculation saturation. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider what happens when you try to run long-context agentic inference tasks. Recent benchmarks reveal that context windows in these scenarios can consume up to 1,000 times more tokens than standard chatbot interactions. This explosion in data requirements forces the hardware into states where memory bandwidth becomes the absolute critical constraint for both temperature management and latency. You might have a processor capable of billions of calculations per second, but if it cannot fetch the necessary context from high-bandwidth memory fast enough, that compute power is effectively useless. The system slows down not because the math takes too long, but because the data pipeline is choked. This reality forces us to reconsider how engineers should approach hardware selection for production environments. For a junior or early career software engineer building real systems, prioritizing raw FLOPS numbers is now a strategic error that will lead to poor performance and unexpected costs. The most important specification to maximize becomes high bandwidth memory, bandwidth, and total capacity rather than the number of tensor cores. Models that exceed available video random access memory trigger driver-level paging operations that move data to system RAM, causing up to 10 times degradation in performance. This creates a severe thermal bottleneck where massive I/O overhead generates excessive heat without delivering any useful computational results. We have seen attempts to mitigate this fundamental bandwidth deficit through novel architectural approaches. Papers on multi-level offloading demonstrate improvements like 2.5 times faster training iteration speeds, yet these solutions merely reduce input-output overhead rather than solving the underlying scarcity of memory throughput. Similarly, proposed architectures like Plena claim 2.23 times higher throughput and 4.04 times better energy efficiency compared to NVIDIA A100s. However, these gains rely on specific, co-designed hardware that is not yet widely available in general-purpose computing environments. The industry currently lacks widespread adoption data for these novel architectures, leaving engineers to choose between theoretical efficiency gains and proven scalable deployment strategies for memory-constrained settings. The physical manifestation of this issue is often misunderstood by those who focus only on clock speeds or core counts. When a GPU operates in a memory-bound state during AI workloads, it must maintain peak clock speeds to maximize data throughput while waiting for information. This turns the graphics processing unit into a heat-generating engine that is starved for data rather than a processor too slow to calculate. The thermal stress you observe on high-end cards often correlates directly with how far they are from their memory bandwidth limit, not their compute saturation point. A card running hot during inference might be throttling because it cannot fetch parameters fast enough, even though the arithmetic units have barely begun working. This creates a paradox where buying the most powerful processor available can sometimes yield worse real-world performance than a slightly less capable system with superior memory architecture. If your model size exceeds what fits in high-bandwidth memory, you are forced into paging modes that introduce massive latency penalties and thermal inefficiencies. The cost of moving data across different tiers of storage becomes so dominant that the actual computation time becomes negligible by comparison. You end up paying a premium for compute power that never gets utilized because the supply chain cannot keep it fed with the necessary weights and activations. The shift in engineering strategy requires a fundamental change in how we evaluate system requirements. Instead of asking which card has the highest teraflops rating, you must ask what is the effective memory bandwidth available per watt and whether your model fits within that capacity without triggering paging operations. Long-context agentic inference highlights this constraint most dramatically because it pushes data movement to its absolute limits. A context window consuming 1,000 times more tokens means the system spends nearly all its time moving information rather than processing it, making bandwidth the single most critical factor for temperature management and latency reduction. As you move forward in your career designing or selecting hardware for production AI systems, remember that compute is no longer the scarce resource. Data movement has become the primary constraint defining performance ceilings. The gap between theoretical peak FLOPS and actual achievable throughput continues to widen as models grow larger and context windows expand further. Understanding this distinction allows you to make informed decisions about where to allocate budget and how to architect systems for real-world efficiency rather than marketing specifications. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.